Hello guys, welcome to the third lecture in series of lectures of rigid body dynamics. In this lecture we shall talk about a very important concept in rigid body dynamics, that's called moment of inertia. So let's talk about that. But before talking that, first let's recap what we learned in the last lecture. So in last lecture I talked about translational kinetic energy and rotational kinetic energy. Now, so in last lecture we learned that if there is a random body, and we know that in rotational motion, either a particle is performing circular motion or it is at rest. Okay, so every point, so I'm just making an axis here. This is the axis of the body in which it is rotating with angular velocity omega. Okay, so every point will be moving in circle. So this is, let's say, point 1, so it will be moving in a circle of radius r1, and the center of that circle would be on the axis. Every point will be moving in a circle at the center. Okay, and because the body is moving with omega, so every point will be also moving with omega. So every point is moving with omega. So kinetic energy, so let me write here. So kinetic energy equals to kinetic energy of first particle plus kinetic energy of second particle, all the way up to kinetic energy of nth particle. Okay, now we can write V as omega into r. So this is half m1 and this is omega r1 square, omega square r1 square, plus half m2 omega square r2 square, all the way up to half mn omega square rn square. Okay, and we can take omega common, because you can take omega square common because it is same in every term. So this becomes m1 r1 square plus m2 r2 square, all the way up to mn rn square. Okay, now this is the term which we said that it is actually moment of inertia, so we called it moment of inertia. This particular combination of mass and distance from the axis, this is moment of inertia. Moment of inertia of first particle, and these all these add up to I of system, and we also call this I. This is I1. Okay, because this is I of first particle, so this thing becomes half. So this kinetic energy actually becomes half omega square into I. Okay, so this is where we got to know about the concept of moment of inertia. And while calculating kinetic energy while calculating rotational kinetic energy, we got introduced to this particular term, and we call this term a new thing, that is moment of inertia. Now let's understand moment of inertia. So this is all just the previous thing with what we recap. Now let's understand moment of inertia in a great detail with illustrative examples. Okay, so let's talk about that. So moment of inertia is represented by the notation used is I. Okay, so let's imagine that there is a body, okay, which has n particles. So I of the system is defined as this, where r is the distance from the axis. Okay, so this is the I of the system. This is a general formula by which you'll find it, but that is the mathematics. What is the concept behind it? What is the physical meaning of moment of inertia? So let's talk about that also. So I'm talking about the physical significance. This is the mathematics. This formula is sufficient for us to find the moment of inertia of every random or every kind of arbitrary of every body of arbitrary orientation. This formula is sufficient for that, to calculate this moment of inertia. But what is the actually the physical significance? So let's talk about that a little bit. That is not actually covered in books, and many people lack the physical significance and its concept behind. So we'll talk about that in detail. So we know that in translational motion, a body with greater mass, let's say there are two bodies, this is m1 and this is m2. If m1 and we apply same force, then if m1 is greater than m2, then m1 will possess a slow start. Okay, इन दोनों में से अगर जिसका मास ज़्यादा होगा, they will offer more resistance to any change because of inertia, because that's what inertia says. Inertia is resistance offered in change of state. तो अगर इन दोनों में से जिसका मास ज़्यादा होगा, that will offer more resistance to change of state. And if m1 is greater, then m1 will possess slow start, because it is offering more resistance, therefore its state will change more slowly. So that is about translational motion. But we know that in rotation, if there is a body, for example, let's say that there is a body of this kind of thing. If this is a fan and this is rotating about this is the axis passing, this is this marker. Let's imagine that this marker is an axis and this is a blades of fan, and there is another blade which is a bit smaller than this. And it is also rotating along the axis perpendicular to it. Then if we apply the same power, which will rotate faster? Now, using this concept that because its mass is distributed because its mass is distributed far from the axis of rotation, and it says that and the moment of inertia is actually product of mass and distance and its distance from the axis. So because the mass is distributed far from the axis of rotation, therefore it will have more moment of inertia. I'm calling it I1, and moment of inertia that this will show along this particular axis, I'm calling it I2. So of course we can looking at this formula, we can actually predict that I1 is greater than I2. Okay, because I1 is greater than I2, therefore we can say that I1 will have a slow start. Okay, therefore we can say that I1 will have a slow start, and it will offer more resistance to any change in state. And the change in state is actually rotations. The body is rotating, so I1 having mass distributions far from the axis of rotation will offer more resistance, and therefore it will offer more rotational inertia, and that's what we call moment of inertia. So that's the physical significance of it. That's why we have seen that that fan with larger blades rotate slowly if supplied same power, and fan with smaller blade rotate relatively faster if applied same power. And we can think a lot about that also, that you can see a tractor wheel. Let's imagine a tractor and a car moving at same speed. So you'll find that wheels of a car are moving faster than wheels of a tractor, simply because the mass distribution is at a greater distance in the wheels of tractor, whereas the mass distribution are closer to the axis in wheels of a car. So that's the physical significance of moment of inertia. Now we shall put some remark for further understanding. So let's talk about that. So here are a few remarks about moment of inertia. So the first remark is that moment of inertia has same physical significance as mass has in translational motion. So in translational motion, larger mass means larger resistance offered to change of state. Therefore, in rotational motion, larger moment of inertia means larger resistance um, uh, offered to change in state of kind of rotational dynamics. So if a body has larger amount of inertia, and it will be difficult to rotate it. Okay, and if a body has a smaller amount of inertia, it will be easier to rotate it. The second remark is that moment of inertia depends on the density of body, mass distribution, axis of rotation, shape and size. I think it is very obvious. If the mass distribution is farther from the axis chosen, it will have greater moment of inertia and therefore difficult to rotate. And if mass distribution is closer to the axis chosen of rotation, then it will be easier to rotate it. If size is larger, again difficult to rotate. Size is smaller, easy to rotate. And I think the second remark is very obvious. The third remark says that in moment of inertia, R1, R2, R3 and Rn are perpendicular distances from the axis of rotation. I think it is also very obvious that while in this particular system, in the previous illustration, we calculated this R1. So this R1 was actually, we all this calculated this body moving in circles. This R1 was actually a perpendicular distance from the axis. So I think that is very obvious too. So now we shall calculate moment of inertia. We shall take few examples to understand this concept more deeply. So let's talk about that. So this is the first example. So we'll solve it. We have to find moment of inertia of these two masses with respect to this axis. Okay, so let's solve it. So we know that moment of inertia is I is defined as sigma m I r a square. Okay, and we can also write this as simply mr square. Okay, where r is distance from where r is perpendicular distance from the axis of rotation. We can write it. So moment of inertia of this particle from the axis will be m into simple the perpendicular distance is d, so d square plus moment of inertia of this particle from axis of rotation would be 2m, that mass, into its distance square, that is 4d square. So I think this is md square and this is 8 md square, so this is 9 md square. That's the I of this two particles. If we consider these two particles part of the system, then the moment of inertia of that system would be 9 md square. This is second example. Again, we have to find moment of inertia. We have to find moment of inertia of this system along this axis. If the axis is passing through the center of the first body, that is of mass m, then we have to calculate moment of inertia. So we can calculate it simply. It's very easy. So I would be, what is moment of inertia of this particle? So we can write m, and distance from the axis is 0, so this is 0. So 0 is 0 square, that is 0 effectively. So this whole thing is actually 0. Write it here. Moment of inertia of this particle would be mass and into distance from the axis. So distance from the axis is 2d, so 2d square is 4d square. So this comes out to be 8 into d square. Okay, so let's take a few more examples to understand this.